Hello, my name is Enrique Nueve, and this is my presentation for Deep Learning Fall 2022 at CU Boulder. The name of my project is Selective Binary Sequence Labeling with the Lovasz Hinge. Starting at the abstract, developments in neural networks have led to models such as recurrent networks, temporal convolutional networks, and transformers, all which are really good at learning conditional, all which have the ability to learn conditional dependencies, and they've seen realized performance. However, the question is open just because it can, will it? Without the right motivation, why would the model learn this necessarily? To motivate this, we need to use loss functions that encourage learning conditional dependencies. However, the theory of loss functions have not kept pace with the development of models. Until recently, just recently, the Lovasz Hinge, a loss which encourages learning conditional dependencies, new theoretical results were published. Particularly, it showed that it's able to learn conditional dependencies when they're defined via a particular type of set function. The challenges previously was that, okay, if you want to learn conditional dependencies, you have to use a set function, yet computationally, it's just not possible. But the Lovasz hinge has shown for a particular class of set functions, polymatroids, this is possible using a set lost Lovasz hinge. However, the initial publication was purely theoretical, and although mathematically rigorous, no experiments were performed. Hopefully, though, it is good in practice because this will open a lot of potential for applications, which is why in this work we explore how well does it perform, particularly for the task of selective binary sequence labeling. All the selective binary sequence labeling is that the model predicts a finite sequence length, and it's going to say for each of the elements, is it true or false? And if it's not confident on any of the elements, it can just say, I don't know. Why could this be useful? For example, in medical diagnosing, let's say you want to learn some conditional dependencies, such as being correct earlier on is better, because if you're correct earlier on, there's more time for medical intervention. But you need conditional logic, a set function to learn this. Furthermore, why just say I don't know? Well, if you say I don't know, it could be a prompt that you need more experts, more doctors to look at the situation instead of automating it through this model. To get into the design of the Lovasz hinge, we go to section 4. Equation 1 is the Lovasz hinge formula. Equation 2 is the Lovasz extension, which Lovasz hinge equation 1 uses. That's where the real power of the method comes from, in that equation 2 converts any polymatroid into a continuous convex function. All that means is it allows you to optimize over said set function, given that's a polymatroid, efficiently, which previously no methods existed. For our experiments, we propose the following polymatroid equation 3. Although notation heavy, all it says is that we prioritize being correct earlier on than later, like the medical example. So we want to see in our experiments, are we correct more often earlier on than later? Moving to our experiments, we performed the task of selective binary sequence labeling over stock data, and the target value was a form of price momentum. We refer to our references of how this is actually constructed. The basic idea, historically, are prices going up or down, and now can you predict this for multiple periods? We predict it for 3 periods ahead. We performed more experiments in the paper, but for this poster presentation, we specifically show our test over Tesla data. We trained it over 5 years of data, and then we verified it. We did a validation set up a month, and then we tested it out for a month. Moving to section 6, results and conclusions. How did we perform? We want to see, are we doing better at earlier periods and later periods? Referring to figure 2, there's 2 variants of Lovasz hinge, one that's risk-seeking, one that's risk-averse. Either version, though, the first period for risk-seeking is accuracy of 87 versus the last period of accuracy of 77, and for risk-averse, it's 88 versus 78. So yes, this results are supporting our claim that our model is prioritizing learning earlier periods over later periods, which is great. Furthermore, referring to figure 2, holistically to just metrics at large, all of them came back very strong, which is great because we didn't know. Again, no one has actually tested this before. This method was just theoretical results. So to conclude, why is this good? Well, although this is not sufficient to conclude the Lovasz Hinge is the next great thing, it is supportive to the claim that these theory results are more than just that, but they can be valuably used for applications where you want to learn conditional dependencies in your model.